All right, we began our investigation into kinematics by looking at a particular scenario that's a car moving across the floor at constant speed, a battery-powered buggy moving in a straight line at constant speed. That's our scenario. Car moving at constant speed in a line. And then we collected data. We chose distances and then measured times. We could have done it the other way around. We could have said, I'm going to time it for 1 second and see how far it goes. It could have been either way, but it's easier based on the technology that I have here and probably that you have. It's easier to choose the distances and then measure the times and then do that multiple times. And then we took that list of numbers and turned it into a picture, a mathematical picture of two values to see how they're related. It's called a graph. And then we put one guy on the vertical axis, the other guy on the horizontal axis, made a scatter plot, and turned that into a picture. And as long as the dots make some kind of systematic pattern, we can then approximate that with a line or some kind of mathematical curve. And then we can turn that into an equation so that we don't have to have a picture. We can summarize it algebraically. And what we hope is that we have dots that will follow some kind of pattern, and then that pattern can be made into a curve, and the curve has an equation that we can then use. So we had distances and times and distances, and then the distances versus the times, and then we had distance as a function of time, some constant times time. In this case, it was the rate or velocity. And then we can look at a new scenario. We can go back through this and then talk about a new event or scenario, and then new data collection, make a new graph, and then see if we can make our equation better. Now, if our equation is already pretty good, meaning the dots followed a very, very solid pattern here, and then when we make the equation, it does a good job of approximating the dots, then when we use that equation to try to predict the next new event, as long as that event follows the same pattern, an object moving in constant speed in a line, it's got to follow, doesn't have to be a car, any object, constant speed in a line. Those are the key features here. As long as it follows the same pattern, we can skip the data collection and the graph making and go straight from the scenario to the equation. And that's what we did in the constant speed problems. We went straight from the event to the equation and then used the equation to determine the missing piece from the event where we only measured 2 of the 3 things. Now what I want to do is use the same pattern here, but for a new event that doesn't follow this rule that we started with. Instead of having an object moving at constant speed in a line, let's have an object move at not constant speed, but still in a line. So what we're going to do is we're going to let a ball roll down a ramp, and we're going to collect data, then we're going to turn it into a picture, and then we're going to turn that picture into an equation, and then we're going to go back and analyze new events that follow the same pattern of what we're looking at now, and skip forward to just analyzing it with the equation. So let's look at that. Here we have our lab set up. I've got my 2-meter sticks set up here, side by side with a little space in between. And I've got my lacrosse ball. Any ball will do. Maybe not a ping pong ball, too light. Maybe not a golf ball because it's got the dimples and that'll mess things up. A tennis ball should be fine. Oh, baseball? I don't know about a baseball. Some kind of ball that's relatively smooth and round should work. A super ball, that should be good. So what we're going to do is we're going to let it roll from rest, and you got to make sure you let it roll from rest all the way down. And so we're going to do the whole meter, and then 80 centimeters, 60 centimeters, 40 centimeters, 20 centimeters, and we want to have enough separation in the distance that we get a clearer picture with our times. If we do it too close together, then the times are not going to be very good here. So let's get our stopwatch, and just like with the car on the floor, we're going to do 3 trials for each because I'm going to assume that my reflexes are not that great. So I'm going to start my stopwatch right when I let go, and you got to make sure that you don't bump it. All right, so. And then write down your times, and then you're going to do exactly the same thing again. 3 times, take the average, like we did before, and if you've got the lab sheet that I provided, then I've also provided the equations to find a few other quantities, the average speed of the ball over the whole ramp, the final speed at the very bottom, because what we're interested in now is no speed, final speed, and then what's the nature of it speeding up over that distance and the amount of time that took. So I'm going to finish taking all the data because we're taking the data in this very similar pattern to what we did last time, so you don't need to see all of that. And then we'll go to the computer and make some graphs using Google Sheets. All right, I've typed in my data here. Took 3 trials for each distance, averaged them together to smooth out some of the error inherent in timing things by hand. And then I used these equations from the top. The same equation that I used before that assumed constant motion. You can always do that, but that won't give you final speed. What that will give you is the average speed. And here, since we have 2 speeds that we can point to, which is the original speed, which is 0, and the final speed, which is what we want, since the original speed is 0, what we can do is we can just take the average speed and double it, and that will give us our final speed since we're starting from 0. And that's very important that you start from 0. And then the acceleration is going to be that final speed divided by the amount of time that it took to get there. And what I want to be doing here is developing this equation. Now, I'm just assuming it here because it's been very well established over many hundreds of years of physics students. Well, first Galileo and other physicists taking data, but then physics students recreating these experiments to verify and show support for these equations. So we've typed in the parts of the data table that we want. We want the time, we want the distance, and we want the final speed and the acceleration. And then we're going to make 3 graphs here. We're going to make one for distance and time, and then final speed and time and acceleration and time. And we'll walk through all of these here and take a look at them. So for the distance and the time, once again, you select your 2 columns that you want to graph, and then go up to Insert Chart. And once again, my computer has reverted to giving me bar graphs. I don't want bar graphs. I want scatter plots. And it's also reverted to putting distance on the horizontal axis, but I don't want distance on the horizontal axis. I want time on the horizontal axis, so I need to switch that. And I want distance on the vertical axis. So now I have this organized properly. And you can see that this is no longer linear. There's a bit of a curve going on here. What we have is for 0 distance, it takes 0 time. But then for that first jump up to 20 centimeters, there's a long time there. So we're going to want to come here to Customize, Series, and this trend line that we add, let's not make it linear because it's not linear. Let's make it exponential. And we'll see what equation that is. Nope, that's not exponential. Power series. That's what I wanted. Power series is what I wanted. Because what I want here is to see what the relationship is between the distance and the time. And you can see my exponent is 1.99. That's very, very good, and that tells us that what we should be doing is squaring the time, multiplying it by some constant, and that will give us the distance. All right, so let's move this out of the way, move to its own sheet. We'll call that distance versus time. And now let's make our final speed versus average time and see what the relationship is there. Once again, we have a bar graph. I don't want a bar graph. I want a scatter plot. And okay, this time they put time on the x-axis and final speed in the series. That's what I want. To customize this trend line, and if you take a look at the dots, you say to yourself, hey, that's pretty, the linear line does a good job of approximating those dots. So we'll leave that as linear. We'll use an equation. All right, and now this says our final speed is going to be some constant times our time plus a very small correction factor. That's an indication that I wasn't entirely successful as always starting it from rest. And I probably should add chart and series titles. So this is final speed versus time. Put that summarization there. Time, that's in seconds. And then I should probably remind myself that we actually measured this in centimeters, not in meters. And we'll move that to its own sheet as well. We'll call this VF versus time. And then our last one now to select two columns that are not next to each other, like I just did there. What you need to do is select one column, then hold down your control key and select the other column. And then you don't have to select the in-between columns. All right, they finally gave us scatter chart, acceleration, time, the appropriate thing. So we don't need to do any fixes. We can just go straight to adding the trend line. And if you look at the trend line, you can see it does a pretty good job approximating these dots. So we're going to leave it as linear, and we're going to use our equation. And now what we have here is acceleration is a very small number times time plus a large y-intercept. So let's put that on its own sheet and label it A versus D. What we have for these three graphs are for the distance versus time graph, it now starts at 0 and curves upward. The velocity versus time graph, it starts at 0 and it doesn't curve upward, it goes upward linearly. And our acceleration graph is a horizontal line. And we'll be looking at the analysis questions in our all downhill lab sheet as we consider these graphs.